Hi everybody, welcome to the start of our energy unit. Energy is a very important concept in physics for many reasons. One, it can be used to do work and thus extract some sort of benefit in society. Two, from a physical mathematical standpoint, energy is one of a number of quantities of nature that are actually conserved. There is a law of conservation of energy. It's one of those very deep principles of nature, along with laws of conservation of momentum, law of conservation of charge, etc. I should mention that there's actually no such thing as law of conservation of mass. It's something that is approximately true and that we conveniently pretend to be true in places like chemistry because it actually is very, very close to being true in chemical reactions. But even in chemical reactions, I mean, you have the fact that, say, a hot material has a slightly greater mass than a cold material because of that extra energy that's latent in the material due to E equals mc squared, that sort of thing. So it's something to keep in mind. But in physics and in all parts of nature, total energy is always conserved. And the fact that it is always conserved, and this is one of the really deep laws of nature that is a result of certain symmetries that exist in nature. In the case of energy conservation, it's the fact that the laws of physics are symmetric with respect to time, leads us to the ability to solve certain types of problems that will always work, even though maybe it won't necessarily be useful to set it up that way, but will always work, at least in principle, because of the fact that energy is conserved. So the rest of this course will be dealing in some way or other with these conservation laws of energy, momentum, and charge. So in this unit, we're going to be dealing with energy and the conservation of energy. So just a quick broad outline. There are a number of different types of energy. There's kinetic energy, and there's gravitational potential energy, there's elastic potential energy. There are actually all kinds of potential energies, and there are even multiple types of kinetic energy, but in this level of physics, we're only going to deal with what we call translational kinetic energy. And then there's work, which is the change in the total energy of a system because of the fact that maybe energy is leaked out of the system into the rest of the universe, or somebody has added energy into the system and thus done work on the system. So energy can come in many forms. There's energy of motion, which is what we call kinetic energy. It can either be translational, which is what we're going to explore in this unit, which is back and forth, up and down, side to side, but we're not going to explore the rotational aspects of it, which are a big deal in AP Physics 1 and AP Physics C Mechanics, basically college-level physics courses. And then there's also potential energy, which is something that can be realized. Think about that word potential. Somebody has this potential or something like that. Well, in the case of energy, it can be realized potentially as kinetic energy. So as we mentioned, kinetic energy is energy of motion. And in this course, we're not going to worry about deriving this, but just note that there is a formula for the kinetic energy of an object which can be derived. The simplest way perhaps of deriving it is with calculus, which is done in particularly AP Physics C, but it can also be derived by considering the area under a graph in this class. In fact, we might take a closer look at this a little bit later, but kinetic energy, we'll just take it for granted right now. There's a formula for it. It's 1/2 mv squared, and that's simply something that you have to memorize. So the kinetic energy of an object, the translational kinetic energy, I should say, which is the only type we're going to deal with, is 1/2 times the mass of the object times the square of the object's velocity. So keep in mind, this means that the velocity is squared, not the mass. So does an object have kinetic energy? Well, ask yourself, is the object moving? If it is, it has kinetic energy. So a quick example of this. What is the kinetic energy of an 80-kilogram football player running at 8 meters per second? Well, you write your givens down. So you have your mass is 80 kilograms, your speed is 8 meters per second. You have your formula, K equals 1/2 mv squared, and plug in the givens. So the next step is, first you write down the formula. The next step is you plug in your givens with units. Notice keep the units. And then at the end, you multiply everything out. Half of 80 is 40. 40 times 8 is 320. Multiply by another 8 will give you 2560. Now notice the units here. The units for energy are joules, symbolized with a capital J. A joule is simply a kilogram meter squared per second squared, because after a while people just got tired of always writing kilograms times meters squared per second squared in their formulas. Now, this also allows us to set up ratio problems. For example, by what factor would the kinetic energy change if mass did not change and velocity was double? So we'll kind of go through the quick derivation of why ratio methods work. So it's like, okay, you have your new kinetic energy. It's 1/2 mass of nu times velocity of new object squared. The old kinetic energy, well, 1/2 times the mass of the old object times the old velocity's object squared. Well, the halves cancel, leaving you with just the ratio of kinetic energies is equal to the ratio of masses times the ratio of velocities, quantity squared. So this method, again, will always work. I mean, here's another way of thinking about it. So anyway, you plug in your numbers, the mass doesn't change, the velocity gets doubled, so the new kinetic energy is 4 times the old kinetic energy because the ratio is 4. So new divided by old is 4, so new is 4 times old. Another way of thinking about this, say, well, okay, kinetic energy is proportional to mv squared. And just remember, whenever you have a proportionality, which can only really work if you're dealing with a product or quotient of things, then you can replace every variable on all sides of the proportionality by the ratio of those variables. And upon doing that, you actually get an equality. So it's like, okay, ratio of kinetic energies is equal to ratio of masses times the square of the ratio of speeds. Plug in the ratios. The ratio of masses was 1. I was a bad physics student here. I didn't write my givens, but ratio of velocities is 2. So the ratio of kinetic energies is 1 times 2 squared, which is 4. So consider this one. How does the kinetic energy change if a car's mass changes by a factor of 1/3 and the car changes its speed by a factor of 4/3? And here when we say the mass changes by a factor of 1/3, we're saying that the ratio of the new mass compared with the old mass is 1/3. So think about that. Maybe pause the video and think about what answer you should get when you do that. Okay, so you have your proportionality. K is proportional to mv squared. So therefore the ratio of k's is equal to the ratio of masses times the ratio of speeds squared. And again, you should write down your givens here and say that m2 over m1 equals 1/3, v2 over v1 equals 4/3, and those are what you end up plugging in. And when you multiply things out, the 1/3 ends up being for the mass. The 4/3 gets squared because the ratio of velocities gets squared. In other words, whatever happens to the variable is what happens to the ratio. So you get a factor of 16/27. So you say that the new kinetic energy is 16/27 of the old kinetic energy. And you just leave it like that fraction, because by saying these fractions like this, we are assuming infinite precision. Now, what about potential energy? There's lots of different types of potential energy. One form that is something that you might already be familiar with from way back in the past, you've probably come across the equation E equals mc squared before. So this is something that we are actually not really going to calculate in this course, but I should simply note that it exists. It's kind of like basically the rest energy of an object, so to speak. But you could think of it as a type of potential energy. So if something had a mass of 1 kilogram, then the amount of energy that you could get by completely obliterating that object would be given by plugging in 1 kilogram in for the mass, and c is the speed of light. C is about 3 times 10 to the 8 meters per second. So square that, you get 9 times 10 to the 16. So a 1 kilogram object completely obliterated would give you 9 times 10 to the 16 joules of energy, which would be about a 20 megaton hydrogen bomb explosion. Now, keep in mind that how are you going to obliterate 1 kilogram of mass? Well, the easiest way would be to interact it with 1 kilogram of antimatter, and then you would actually end up getting twice this much energy because you're actually obliterating 2 kilograms of mass. So anyway, or I guess you could obliterate 1 kilogram of mass by having half a kilogram being matter and the other half being antimatter. So what is antimatter? Well, it's not the wife of Uncle matter. It's simply matter that has certain types of properties that are inverses of the properties of ordinary matter. Okay, but we won't really have much to say about it in this course, except maybe when we talk about modern physics near the end. The types of potential energy that we will consider in this unit are gravitational potential energy and elastic potential energy. Gravitational potential energy comes from raising an object to a certain height relative to a reference point. Elastic potential energy comes from either stretching or compressing a spring. So, more formulas. Yay, we like formulas because they allow us to do things, and they always work when assuming that the conditions are right. The formula that we're going to use for gravitational potential energy is U sub G equals mgh. Now U, capital U, is generally the symbol for potential energy. Just as capital K is the symbol for kinetic energy, the symbol for potential energy is capital U. But since there are lots of types of potential energy, it is appropriate to use a subscript. So I use the subscript U sub G. So U sub G equals mgh. The mass of the object times the acceleration due to gravity times the height. Now, just to be honest and completely forthright, this formula is not exactly correct. The real equation is U equals negative big G, big M, little m over R. But as long as the height by which you are changing is small compared with the radius of the object giving you the gravitational field, in this case Earth's radius, then you can use this formula as a good approximation. So, it's usually convenient to pick a reference point. For example, I often pick mine as the lowest point in an object's motion as saying, hey, that's what I'm going to call h equals 0. A lot of people just pick it as Earth's surface, but it really just depends. You should pick the most convenient possible reference point so that you don't have to do too much subtraction. So, with that in mind, maybe work by yourselves. So, on these problems, first you have a 7.3 kilogram gallon of paint lifted to 1.78 meters vertically. What's its change in potential energy? And next, a roller coaster of 465 kilogram mass rolls up a hill with a vertical height of 75 meters. What's the change in potential energy relative to the ground? Notice that what we really care about here is not the actual value of potential energy, but the change in potential energy. We will often pretend that it's the actual value by just calling it U, but technically what we're actually calculating is a delta U equals mg delta H. So even though that might not be clear in these solutions, that is what we're really doing. So in the case of the first one, I think these are simple enough that I don't need to show it step by step, so I'm just showing it all at once. So you have the mass is given, the height is given. Use the formula U equals mgh. Plug in the mass, the acceleration due to gravity, and the change in height, and you get a change in potential energy of 127 joules. Again, technically this is a delta U, not a U. It's technically a delta U, just as technically this is a delta H, but we're just going to pretend that these are U's and H's. And then in the next problem, you have the mass, 465 kilograms, change in height of 75 meters, so the change in potential energy is mg delta H. So you get U equals m, plugged in, G plugged in, delta H plugged in, and that becomes 3.42 times 10 to the 5th joules, or 342,000 joules, whichever you prefer. Now, there is also elastic potential energy, the energy of a spring when you compress or extend a spring. So, there's an equation for that, and again, we can derive that equation by considering the area under a graph. We will do that later this unit by using the fact that the work is equal to the area under a force versus position graph. But for now, we will just take it for granted that when you compress or extend a spring that behaves in a normal way, by what I mean by that I'll mention soon, then the potential energy in that spring is 1/2 kx squared, where x is how much you have compressed or extended the spring from what we call its equilibrium position. K is something called the spring constant. K is big for very stiff springs. K is small for very loose springs. So it's something to keep in mind. Okay, now this only works if your spring is what we call a Hookean spring. There's a nice word for you. What is a Hookean spring? Well, a Hookean spring is a spring that obeys Hooke's law. Well, what is Hooke's law? Hooke's law is the law that applies to Hookean springs. Okay, great. What is it really? Hooke's law says that the force necessary to compress or stretch a spring is directly proportional to the distance that you want to compress or extend it from equilibrium. So if you just take a spring and leave it alone, then it's in equilibrium. If you stretch it by, say, 1 centimeter, that requires a certain amount of force. Hooke's law says that it requires twice that much force in order to stretch it 2 centimeters. 3 times that amount of force if you want to stretch it 3 centimeters, etc. In other words, Hooke's law says that the force is proportional to the distance you want to compress or extend it. The proportionality constant is that Hooke's constant, that thing that tells you something about the stiffness of the spring. Now notice there's a negative sign there. What does the negative sign mean? It means that if you've stretched the spring, the force tries to bring it back. If you compress the spring, the force wants to bring it back. It wants to re-extend it. If you compress it, it wants to compress it back if you extend it. So that's what the minus sign there is for. In this unit, what we are going to care about is the magnitude of that force, because what we care about is the magnitude of the potential energy. Now, the units for the spring constant are what we call newtons per meter. So in other words, just how many newtons of force must you apply in order to stretch it a certain number of meters. So let's take a look at an example. So if a horizontal spring with a spring constant of 860 newtons per meter is loaded with a large clock of 52 kilogram mass and compressed a distance of 2.5 meters from equilibrium, calculate the elastic potential energy and calculate the magnitude of the force necessary to hold this position in the spring. Well, we write our givens. So we have K is given, the mass is given, the compression distance of 2.5 meters is given. So there we go. Well, there's the equation for our elastic potential energy, U equals 1/2 kx squared. Plug in the K, plug in the X, and you get 2,690 newtons of, that should say 2,690 joules. So we need to fix that, and it's fixed. Now for the force, again we use Hooke's law, so we have F equals kx. So plug in the spring constant K, the magnitude of F equals the magnitude of kx. Plug in the spring constant K, plug in the compression distance, and you get the amount of force necessary to do that. And that's a lot of force. That's like almost 500 pounds. So that's a pretty decent spring constant. But then again, you are trying to compress at a large distance. So now, consider these problems. So what's the potential energy of a spring compressed 0.53 meters from equilibrium if the spring constant is 210 newtons per meter? And what's the spring constant of a spring that is stretched 123.2 centimeters while storing 93 joules of energy? So work with each other. So if you're watching this video, you might be alone, so I don't know, maybe go outside, find somebody random off the street and have them watch the video with you and work with them on the problem. So get other people into this. So in any case, with the first problem, the potential energy of that spring, so you have a compression distance of 0.53 meters and a spring constant of 219 newtons per meter. Plug in the numbers, and you get 31 joules. Notice that we write our formula first, plug in our numbers with units. Now, what you'll see here is that it's like, okay, you have newtons per meter in the first unit, and then meters squared in the second. So newtons per meter times meter squared, that's a newton meter. Well, apparently a joule is also a newton meter. Well, I thought a joule was a kilogram times a meter squared per second squared from the kinetic energy formula. Well, think about it though. A newton, F equals ma, is a kilogram times a meter per square second. So you multiply by another factor of meters and you get kilogram meter squared per second squared. That's the same thing as a newton meter. Either way, it's a joule. For the next problem, don't forget you got to convert to SI units. So meters for distance. So that distance is 1.232 meters. The elastic potential energy is 93 joules. So solving for that spring constant, we obtain 120 newtons per meter. Okay, now something to consider is that in a perfect world, the conservation of energy applies regardless. You don't have to worry about energy being added to or subtracted from your system. But let's consider how we're going to think about this in the future. Think about problems like this. So in this situation, question is, if a ball starts from the top of each of these three differently shaped hills, or is simply dropped, how do the potential energies compare at a height halfway from the bottom? Well, the shape of the hill doesn't change anything about the absolute height. It might change how long it takes to get to that height, but it doesn't change anything about the actual height. And all that potential energy cares about is the actual height. So, in other words, we don't really care about the shape of the hill. In each situation, the potential energy will be exactly half of what the potential energy was at the top. So, that's something that we're going to keep in mind when we solve other problems, like, for example, if the ball starts from rest at the top, how will the speeds compare at the bottom? Well, one of the big principles of conservation of energy that we're going to get to is the fact that total energy is conserved. So if you decrease potential energy, or at least if you decrease in gravitational potential energy, then you must have increased in some other some other kind of energy, either some other type of potential energy or in some kind of kinetic energy, whether translational or rotational or both. But in this class, it's always going to be translational. So again, in this case, the hill shape has nothing to do with MGH, so the speeds are going to be the same at the bottom, no matter what. Of course, the shape of the hill will control how long it takes to get to the bottom, but if there hasn't been any energy lost from the system due to friction or something like that, then your velocities, your speeds at the bottom at least, are going to be the same regardless. So let's take a look at some simulations. In each of these simulations, we're going to have an illustration of this interchangeability of energy, but total energy being constant. So in this simulation, we have a roller coaster where we have a ball on a quote roller coaster of a quartic shape. Now, I'm going to raise it to a slightly different height here, and I'm going to have it show the energy. So here you have an energy graph, and I'm also going to change the time rate to 0.50 so that we can see it going more slowly. But you have an energy graph right here. Notice that the total energy is always the same. When it's at its greatest height, it's all potential energy, given by the darker gray. When it's at its lowest height, it's all kinetic energy given by the lighter gray. But notice the lighter gray goes away once you get to the top of the coaster. Whereas when it reaches this point in the middle, some of it's kinetic energy and some of it's potential energy. But the total energy is constant. How about in this next one? In this case, we have a one-dimensional spring. When we turn on our energy, we have a total energy being constant, but the kinetic energy, in the middle is when the kinetic energy is at its largest. Let me change that time rate, 0.50. So when it's in the middle, you have maximum kinetic energy, where, in other words, where the spring is not stretched or compressed, so no potential energy in the middle, but at the end it's most stretched, so you have all potential energy at the end, and you also have all potential energy at the other end where it's most compressed. And meanwhile, with a two-dimensional spring, here, when I show the energy, we have it going back and forth the same way as before, but in this case there are multiple kinds of potential energy. You have potential energy due to gravity, and you also have potential energy due to the spring. And there are some times where, since it's a two-dimensional spring now, it's mainly kinetic energy when it's kind of just, when it did that rocking back and forth bit, which it'll probably end up doing again in just a minute. So, in fact, you can kind of see that when that happens, the potential energy bar doesn't go all the way that way. So it's somewhat of a chaotic system. So it's kind of cool. So now that you've seen all of these, what I would like you all to do is summarize what you've learned on a piece of paper or in your notebooks, because these facets are what we are going to explore as we continue into this unit, starting with the next video.